Bismillahirrahmanirrahim. Welcome to the channel Electrical Engineering. In this lecture, I am going to discuss in a deep way the various expressions of power and the torques across the induction motor. So these are the losses which are taking place in the induction motor, and this is the simplified equivalent circuit. So first of all, based on this figure, I will try to solve a very simple example problem. In this problem, we are given a 480 volt induction motor operating at 60 Hz and 50 horsepower is the output power. The motor is drawing 60 ampere current at 0.8 power factor lagging. The stator copper losses are given as 2 kilowatts, rotor copper loss is given as 700 watts, the friction and windage loss is given as 600 watts, and the core losses are given as 1800 watts. So the input power can be calculated using this expression. All these quantities are given. So it is equal to this 42.4 kilowatts. The air gap power is equal to input power minus stator copper loss minus core loss, which is evident from this figure. So this is air gap power. After subtracting stator copper loss and core loss from this input power, we get the air gap power. So after subtracting rotor copper loss from the air gap power, we can obtain P converted. So this is P converted and it is equal to 37.9 kilowatts, and P out is equal to P converted minus P friction and windage loss. So this is P out, and since 1 horsepower is equal to 746 watts, so 37.3 kilowatts is basically analogous to 50 horsepower. So efficiency of this motor is equal to P out over P in, and P out is 37.3 kilowatts, P in is equal to 42.4 watts. So the efficiency is 88%, which was the objective of this problem. Now we will see various expressions of powers and torques in induction motor. The stator copper loss is equal to 3I1 square R1, the power dissipation across the stator resistance. Similarly, core loss is equal to 3E1 square GC. GC is the conductance of the resistor which is present at this shunt branch. So GC is the reciprocal of this RC, and if we multiply this GC with this E1, we will get the core loss. And air gap power is equal to this expression, and air gap power is also equal to 3I2 square R2 over S. So this is the power which is dissipated across this branch or across this component at the rotor side. Now the rotor copper loss is equal to 3I2 square R2. Okay, so this is the power which is dissipated across the rotor winding. Now P converted is equal to air gap power minus the rotor copper loss. And if we subtract this expression from this, we will get this simplified expression, and this is the expression for the converted power. And from these two expressions, we can say that rotor copper loss is equal to S times air gap power. Okay, so rotor copper loss is equal to S times air gap power. So P converted is equal to PAG minus SPAG. So it can be represented by 1 minus S times PAG. So this is also P converted. And induced torque is calculated by P converted over omega M. And P converted is equal to 1 minus S into PG, and omega M is equal to 1 minus S omega S. Okay, so these 1 minus S terms will be cancelled out. So another expression for the induced torque is the ratio of PAG to omega S. So these two expressions are identical, and P converted over omega M or P air gap over omega S, both are equal. So if we see this figure, here at this stage we have air gap power, and at this point only the magnetic field is revolving at a synchronous speed omega S. So at this stage, the induced torque should be equal to the power at this stage, which is air gap power divided by the speed, which is omega S. So if we move at this stage, we have the power which is P converted, and here we are present at the rotor side, and the speed of the rotor is actually omega M. So induced torque is equal to P converted over omega m at this stage, and also induced torque is equal to air gap power omega s at this stage. So both quantities are identical, and that's why we have obtained these two expressions. So from equation 1, this is the equation 1, we can say that 3I2 square R2 into 1 minus S over S is equal to P converted, which is given over here. So this R2 into 1 minus S over S uh, can be assigned a new name, which is R converted. So R2 into 1 minus S over S is basically equal to R converted. So this R converted is equal to R2 over S minus R2 if we multiply and simplify this quantity. So now from here R2 over S is equal to R2 plus R converted. So this R2 can be shifted to the right hand side. So this R2 over S will be equal to R2 plus R converted. So here we had only one resistance at the rotor side, but this R2 over S is equal to R2 plus R converted. So we can replace this single variable resistor with two resistors. So this R2 over S is equal to R2 plus R converted. So this is R2 and this is R converted. So actually this is R converted, and R converted is equal to R2 into 1 minus S over S. So there is no S term over here, so that will be a fixed resistor, but we have S terms over here, so that will be variable resistor. Now, what is the purpose of isolating or of dividing this R2 over S into two resistances? Now, we can see that the power which is dissipated across this R2 resistance is called rotor copper loss, and the power which is dissipated across this R converted is called the converted power, which is P converted. And the sum of these two powers, P rotor copper loss plus P converted, is equal to air gap power. So the total power which is dissipated across these rotor resistances is called air gap power, and air gap power is equal to rotor copper loss plus P converted or converted power. So this is actually rotor copper loss, and this is the P converted. So this is the power which is actually converted to the mechanical power. So this is I2, which was derived in the previous slide, and it is reproduced over here. And air gap power is equal to this expression, and this can be represented by this equation if we substitute the value of this I2. And induced torque is equal to air gap power omega over omega s, and this is equal to this expression. Now the source impedance is equal to R Thevenin plus JX Thevenin plus JX2. Now we have to calculate the maximum torque which can be obtained from the induction motor. So in order to calculate the maximum torque, we know that the torque will be maximum when the power dissipated across the rotor is maximum. So we will apply the maximum power transfer theorem in this equivalent circuit of the induction motor, and then we will calculate the maximum power, and then we will calculate the maximum torque or pull out torque. So this rotor, the power dissipated across the rotor is actually the power which is dissipated across this branch. So apart from this R2 over S, there are three other components. We can ignore this shunt branch. The other three components are R1, JX1, and JX2. So if the impedance of these three components becomes equal to this resistance, then we can say that maximum power will be delivered to the rotor. And at this condition, the torque which is produced by the motor will be maximum. So in that condition, Z source which is equal to this, and that should be equal to R2 over S. So this is the condition for maximum power or the maximum torque. So from this expression, we can calculate S max. So S max is the slip corresponding to the maximum torque, and it is equal to R2 over this expression. So when we substitute this value of R2 over S in this expression for the induced torque, we will get the formula for the maximum torque. So R2 over S is equal to this. This is the condition for maximum power, and this R2 over S can be substituted over here and over here. And after doing the simplification, we get this maximum torque, and its expression after the simplification is written over here, and it is equal to 3V Thevenin square over 2 omega S R Thevenin plus R Thevenin square plus X Thevenin plus X2 whole square. Now, if we want to see further the torque speed characteristics of the induction motor, such curves are obtained for various values of rotor resistances. Now, this plot is obtained for induced torque versus omega m. So, in that case, we have omega m which is increasing from 0 to omega s, from left to right. So, in this case, the slip actually is varying from right to left. So here at this point, when omega m is equal to omega s, the slip will be equal to 0. And at this point, when omega m is equal to 0, the slip will be equal to 1. So in that case, such curves are obtained. And secondly, this curve is actually the flipped version of the curve which I showed you in the previous lecture, because in that case the induced torque was plotted as a function of slip. So in that case, slip actually was varying from left to right. Here we are actually plotting this induced torque as a function of omega m. So in that case, the slip will be opposite. So this point at which the slip is equal to 1 corresponding to the starting torque, and secondly, when omega m is equal to omega s, there is no relative difference between the speed of the rotor and the synchronous speed, or we can say the rotor is actually running at the same speed as the magnetic field, and there is no relative motion between the rotor and the magnetic field. So that's why there will be no induced current, there will be no induced emf, there will be no current, and there will be no torque. So that's why when we have zero slip, the torque will be equal to zero. So these are the starting condition, because at this point the slip is equal to 1, and at this point omega m is equal to 0. This is the starting torque. So when we have higher value of rotor resistance, which is R5 is the maximum value of rotor resistance, the starting torque is maximum. When gradually we reduce the rotor resistance from R5 to R4, the starting torque becomes smaller, and so on. So for R3, it is decreasing, R2 and R1 is the value for which the starting torque is minimum. But the maximum torque or pull-out torque is constant in all the cases. So it means that the maximum torque or pull-out torque is actually independent of the rotor resistance, which we can also observe in this expression. So in this Tmax, we don't see any R2 term over here. So it means the maximum torque is independent of the rotor resistance, but the maximum, but the slip for the maximum torque, okay, so the slip corresponding to the maximum torque is different in all these cases. So for this R1, the slip corresponding to the maximum torque is smaller, and this R2, the slip is slightly higher. So S max actually depends on the rotor resistance, so which can be observed in this expression. And also the starting torque actually depends on the rotor resistance. So the expression for the starting torque is the same expression which we can see over here, but with the only difference of this S. So if we substitute this S as 1, so if this S is equated to 1, this expression will become T start. So it will become T start. So T start is actually depending on R2, and S max is also depending on R2, but this maximum torque actually doesn't depend on R2, which is visible in these characteristic curves. So this is the pull-out torque or maximum torque, and it is 100% at this point. Here it is 2%, 200%, and it can go up to 500 to 600% when the torque is maximum. So now we are going to discuss the mathematical derivation of this Tmax when we substitute this R2 over S in this induced torque formula. So this mathematics is shown in this slide. Okay, so this is induced torque and this is R2 over S. So now we are going to substitute this R2 over S over here and over here, and then we will start doing the simplification. So this is V Thevenin square, and in place of R2 over S, we have put this equation, and this is omega S. This is R Thevenin. This is R2 over S square. So R2 over S square means this whole expression and its square. So uh, so this R2 over S whole square and x7n plus x2 whole square. So this is the expression that we have obtained. Now we have to expand this square. Okay, so a plus b whole square is equal to a square. Okay, plus b square. So the square of this term, it is actually, we can see the disappearance of this square root, plus 2ab, 2 times this term multiplied by this term. So 2 times this term multiplied by this term, and this term which is uh, also present over here. So now this R Thevenin square plus R Thevenin square, it will become 2 R Thevenin square. Here we have 2 R Thevenin into this, and this X Thevenin plus X2 whole square, and this is X Thevenin plus X2 whole square. It will become 2 X Thevenin plus X2 whole square. So we can see 2 which is present with all these terms, so that 2 can be taken as common over here. And in the inside of the bracket, we will get R Thevenin square plus X Thevenin plus X2 whole square plus R Thevenin multiplied by this under root term. Now we are going to take this R Thevenin plus X Thevenin plus X2 square under root term as common over here. And when we do this practice, that R Thevenin square plus X Thevenin plus X2 square under root, that term will be cancelled out with the term which is taken as a common over here. And here we will get only R Thevenin term, because this term is taken as common and it is cancelled with the term in the numerator. We will get only this R Thevenin, and this term, we will get a square root of this term as a result of taking this term as a common. So this is the same expression which I have already shown you in this slide. So 3v Thevenin square divided by 2 omega s and this. So this is the equation for the maximum torque, and these are called the torque speed characteristics, which are shown again over here. This is the starting torque, this is the pull out torque, and now we are going to plot these torque speed characteristics in Matlab. Okay, so when we go to Matlab, you can see this is the stator resistance. Okay, this is stator reactance, this is rotor resistance, this is rotor reactance, this is magnetizing reactance, and this is the phase velocity, synchronous speed, and omega s is equal to 2 by ns over 60. And this is V Thevenin. Okay, so V Thevenin is equal to this term, so V5 multiplied by xm over square root R1 square plus x1 plus xm whole square. And this is Z Thevenin, which actually we derived in this lecture. And R Thevenin is the real part of the Z Thevenin, X Thevenin is the imaginary part. Now we are plotting this torque speed characteristic with as a function of slip. So this is the slip. I am going to vary this value of slip from 0 to 1. But the first value, which is actually 0, is replaced with 0.001, because if we don't do this, the slip will be equal to 0 for the first term. And if the slip is 0, that induced torque will be calculated as infinity. So this slip, since it is coming in the numerator, in the denominator, so that cannot be 0. So we have to make it very very close to 0, but don't equate it exactly equal to 0. Otherwise this induced torque value will be undefined. So we are sweeping this slip term from 0.001 to 1. Okay, so this is the mechanical speed, which is 1 minus s into ns. So this is the loop which is calculating the induced torque, and here we can see expressions for V Thevenin, R2 over S, omega S, and other quantities. And the second calculation is actually that of the induced torque for the double of the value of the rotor resistance. Here we have resistance R2, here we have the resistance of 2R2. Okay, the resistance at the rotor side is doubled and all other terms are the same. So these are the plotting commands, and then we will try to verify the plots with the mathematical expressions of a starting torque and the maximum torque. Okay, so when I run this file, such a plot is obtained. Okay, so here you can see the rotor resistance is equal to R2 for this solid line, and this rotor resistance is 2 times of R2 for this dashed line. So this curve is actually very much identical to the curve which we have seen in these lecture notes. Okay, so these curves can be compared with each other, and you can see this is the starting torque and this are the maximum torques. So for two different values of rotor resistances, and now let's check the value of starting torque and the maximum torque. So maximum torque is 230.8, so we can verify its value from this curve. So let's click on this marker, and now let's click over here. So this maximum torque is actually 230.8, which is calculated by this analytical expression. Similarly, if I click over here, it is 230.8, which is the maximum torque, and it is exactly the same for both the values of rotor resistances. Now let's say verify the starting torque for R is equal to R2. The starting torque is equal to 106.6, and the starting torque for the double of the value of rotor resistance, the starting torque is 174.1. So all these values are in good agreement with the graphical results, and this starting torque is basically calculated using this same expression, but this s is actually replaced by 1. So you can see we don't have any R2 divided by s term, so only R2 terms are here. So when s is equal to 1, this expression will correspond to the starting torque. So I hope you have enjoyed and understood the contents of this lecture. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.